Hello, welcome back to our channel. Today we are going to discuss about the nuclei chapter. It is also very easy chapter. Don't leave this chapter for MSET, mains and as usual for NEET. Then come to our topic. What is the nucleus? Nucleus is the combination of protons and neutrons. But where is the nucleus? It is inside the atom and it is occupied center of the atom. And what is the charge of the atom? Charge of the atom, neutral. But the charge of the nucleus is a positive charge. So always you can say that nucleus is the combination of nucleus is the combination of protons plus neutrons. Protons are having which charge? Positive charge. For neutrons, no charge. These are the chargeless particles. Then we are going to remember that Z is the atomic number. Z is the atomic number and it is nothing but number of protons. This is the number of protons. And A is the mass number. A is the mass number. It is the combination of both protons and neutrons. So you can say that number of protons plus number of neutrons. Then A minus Z is giving the number of neutrons. So any atom we are representing X atom. Instead of X you can take it hydrogen, helium, lithium, anything you can take it. But you remember that atomic number we should write here and mass number is like this. So any element we can represent like this. Now we are going to the types of nuclei. How many types of nuclei are there? There are 4 types of nuclei are there. First one is the isotopes. Isotopes means same atomic number is represented by Z and different mass number. What is the example for that? H11, H12, so on you can take it. See, look here, atomic number is same but mass number is different. This type of atoms are called this type of nuclei are called nuclei is the plural, are called the isotopes. So this type of questions also they will ask that. Then second one is the isobars. What are the isobars? Same mass number but different atomic number. So what you are giving that example? Suppose you are taking N714, C614, like that you can take some elements like that. So here just you can observe that mass number is the same, atomic number is the different. Then next one is the isotones. What are the isotones? Different mass number and different atomic number, but same number of neutrons. Suppose we are taking O816, then F919, O816, here 8 you are getting, O919 we are taking, but another way simply you can take it. This is the X element, here atomic number is the Z1 you can take it, here mass number is the A1. Another one Y we are taking, atomic number is the Z2 and mass number is the A2. But here A1 minus Z1 equals to A2 minus Z2 you can take it. In periodic table you can take any atoms, like you should see that which are the isotopes, which are the isobars and which are the isotones. So this is the same atomic number, this is the same mass number. Here mass number is different, atomic number is different, but number of neutrons are same. So these are called the isotopes. Then fourth one is the isomers. So here same atomic number, same mass number, but different radioactive properties. That type of nuclei are called the isomers. So these are the types of the nuclei. Then we are focusing on what is the size of the nucleus. Already you know that atom is having the spherical shape and nucleus is also having the spherical shape, and nucleus is the combination of both protons and neutrons. That's why you can treat it that nucleus is having the positive charge. Now we are focusing on what is the size of the nucleus. Then what is the relation between radius of the nucleus and mass number? See, always you should remember that when we can go through the size of the nucleus, we can give the relation between volume and mass number. You know that mass is directly proportional to volume. So here you can write it when we are going through the size of the nucleus. See, mass number is directly proportional to volume. So A is, you know that is having the spherical shape, means 4/3 pi r cube we are taking. So then A is directly proportional to r cube. A1 by A2 equals to, we can write it R1 by R2 whole cube. Then R1 by R2 equals to, what we are taking, A1 by A2 whole to the power of 1 by 3. While both the sides we can take the cube root. This is very, very important formula. We do one problem also. Suppose if A1 equals to 8 and A2 equals to 27, compare the radii of nuclei, means immediately we can go through the ratio of this one. So 8 means 2 cube, 27 is the 3 cube, 1 by 3. So cube cancel. Answer is how much? 2 by 3. So this is the relation between mass number and radius of the nucleus. Then we are going to discuss about here. Here R A is directly proportional to R cube. It should be right, R cube is directly proportional to A. From this you can express, when you are removing that proportionality constant, R equals to R naught into A to the power of 1 by 3. This R naught value is 1.4 into 10 to the power of minus 15 meters, or you can say that 1.4 Fermi also. 1 Fermi equals to, what do you say that? 10 to the power of minus 15 meters. Like 1 angstrom equals to 10 to the power of minus 10 meters. Like nano, pico, like that different things are there. But here when we are going to the size of the nucleus, you can express this. This R naught is this one. Suppose we are doing one problem. If A equals to 64. Find the radius of that particular nucleus. See, now we can able to find out the nucleus. R equals to, R naught is how much? 1.4 into 10 to the power of minus 15. So here A cube, 64 we can write it 4 cube also. 1 by 3. This one cancel. Finally we are getting 6.4 into 10 to the power of minus 15 meters, or 6.4 Fermi also you can take it. Like that we can find out the radius of the any nucleus with the help of this one. Then after that we are focusing on which unit is suitable for finding the mass of the nucleus. You know that before that, for finding the mass, when we are going to the gold shop, we are asking in terms of the grams. When we are going to the vegetable market, we are asking in terms of kgs. When we are going big weights, metric tons, like that we are taking. So here these are suitable for somewhat big physical quantities like that. When we are finding the mass of the proton, mass of the neutron, mass of the electron, mass of the atom and mass of the nucleus, they discovered one more unit. For comfortably we have to find out that one, that is the atomic mass unit. So while finding the mass of the nucleus, they have introduced one more unit, that is the atomic mass unit. You remember that 1 AMU equals to 1/12 of the mass of the carbon C612 atom isotope. So this is the atomic mass unit. Then what is the relation between atomic mass unit and kgs? See, 1 atomic mass unit equals to, small letter also you can take it, nothing will happen, 1.67 into 10 to the power of minus 27 kgs. 10 to the power of minus 27 kgs. You know that from the Einstein's relative theory, E equals to mc square. So how can you say that energy of this one? See, E equals to mc square, mass into velocity of light square, we are getting, this is in terms of joules. Suppose this is in terms of joules. This mass is in terms of atomic mass unit. What we are taking here, mass is in kgs. When we are taking in terms of atomic mass unit, how can you find out the energy? Simply you can take it AMU into that mass into M into 931.5 million electron volts. Million electron volts. Suppose you want to express this is in electron volts, means instead of M we should write it the 10 to the power of 6 also. Very useful unit. Remember that when that options, all options are in terms of million electron volts, means you should multiply the mass with how much? 931.5 million electron volts. Suppose they are asking in terms of joules, means directly you can go through this. So this is the how to find out the mass of the nucleus and mass of the constituent elements also we are using this unit. Now we are focusing on what is the density of the nucleus. You remember that density of the nucleus is the constant. General formula for density is how much? Mass per unit volume. So this is constant, and here you remember that 1.45 into 10 to the power of 17 kg per meter cube is the density of all atoms, not only all nucleus, not only this one. Okay. Now we are focusing on what is the mass defect. What is the mass defect? Look here. We are taking mass of the nucleus. Mass of the nucleus is Mn. Generally what we are saying Mn. Mn is formed by protons and neutrons. Generally what we are taking 5 plus 5, 10 like that. So here also nucleus is the combination of protons and neutrons. When we are focusing to find out the mass of the nucleus, generally what we are thinking, it is the total mass of the protons plus neutrons like that. But in this case what we are saying, generally Mn equals to how many number of protons are there? Atomic number. Each proton mass we are taking ZMP plus number of neutrons are the A minus Z. Mass of each neutron you can say that. But in this case what happens? Always mass of the nucleus is less than mass of the constituent elements. Constituent elements, where that mass gone? Look here. These are the protons, these are the neutrons. When these are combined together, what happens? Inside we can observe the positive charge only. Between proton and proton we can observe the repulsion, even though we should observe that nucleus is the combination of protons and neutrons. What happens here? When the constituent elements are forming the nucleus, some mass is converting into energy to hold the nucleons together. That's why mass is converting into energy. We can observe a little bit mass defect in this case. So that is belongs to the mass defect. Then we are focusing on binding energy. Binding energy. What is the binding energy? See, just now I said we require some energy. We require minimum energy to hold the nucleons together. That energy is called what? Binding energy. Reverse also you should think that what the minimum energy required to break that nucleus into its constituent elements, that is called the binding energy. Then packing fraction. Packing fraction means binding energy per nucleon. It is the ratio of binding energy per nucleon is called the packing fraction. So these are the belongs to mass defect and binding energy. But what is the formula for mass defect? Look here. Mass defect is represented by delta M. Simply you can take it ZMP plus A minus Z into Mn minus mass of the nucleus. The difference between mass of the constituent elements and this mass of the nucleus is called the mass defect. It is represented by delta M. Like that, how to find out the binding energy? Binding energy is the delta M into C square. Same, it is in atomic mass unit, means in terms of million electron volts we should multiply with 931.5 million electron volts. You can express million electron volts, you can express electron volts, and you can express joules also. But it is in terms of kgs, means we can take it C square. Otherwise, if it is in terms of atomic mass unit, means we are multiplying here delta M with the 931.5 million electron volts. So this is about the mass defect and binding energy. Now we are focusing on variation of binding energy. with mass number. Mass number is represented by A. Actually, this is the graph. This is the graph. Here we are drawing the graph between on y-axis, on x-axis. On x-axis we are taking the mass number, that is represented by A, and y-axis we are taking the packing fraction. Simply we can say that binding energy per nucleon. Now you look here. For small elements, what happens? See, like proton, deuteron, H12, then like that, what happens for small elements? Binding energy is very less, so stability is also very less. So like that, when we are increasing the mass number, binding energy also increases. Here we can observe some nicks are there. Then finally you can get the graph like this. Actually, which element is having the more binding energy, more stable, means iron you can take it. And which are the low stability, means you can consider both lighter molecule, lighter atoms, and uranium 92-235, heavier atoms also, thorium, plutonium, all belongs to heavier, and those are having the less binding energy. Then come to this point, few points. If A is in between 28 and 138, those atoms are having the more stable. Then look here. Here lighter molecules are there, no? So these what happens, not in stable condition, means they are participating into the nuclear fusion process. Fusion means two lighter nuclei combined together. It gives the stable single nucleus, that is called the nuclear fusion. Then heavier, in the case of heavier atom, what happens? These are participating into the nuclear fission process. Fission means heavier nucleus is split into approximately two nuclei along with neutrons and along with some energy, that is called the fission process. Here we can observe some nicks are there. Suppose this is helium, He24. This is the lithium. Here what happens? Generally after helium, lithium is coming. But in few elements what happens, especially in the case of lithium, lithium is having the less binding energy comparing with the helium. At that time we are showing this type of this nicks. So this is the variation of binding energy with mass number. Now we are focusing on what is the nuclear force. You know that this is one of the basic force. There are two types of nuclear forces also. One is the strong nuclear force, another one is the weak nuclear force. So whatever the nuclear force, what we are saying? We are saying it is the shortest, short range and strong force comparing with all basic forces. Which is the strong force, means what do you say? Strong nuclear force is the strong one, but it is short range. Inside the nucleus or neighbor atoms nucleus only we can observe this one. So this is short range force, and but it is a strong force. And always you remember that this is the between the nucleons we can observe the nuclear force, means it is attractive only, no repulsion. Between proton, what happens? That electromagnetic force is acting. At the same time nuclear force is also acting. Between the neutron, depends on the distance. Between the neutron also attractive force is acting, that is called what? Nuclear force. And this is a spin dependent one, and inside the nucleus we can observe this type of force. Then we are going through the natural radioactivity. Natural radioactive decay. See, generally what happens, if the atoms are not in stable condition, so naturally those are participating into the disintegration process. So these are giving alpha rays, sometimes beta rays, sometimes gamma rays. Finally these are getting the stable nature, that is called the natural radioactive disintegration. In this first thing is the alpha decay. First one is the alpha decay. Whenever it is participating into the alpha decay, suppose you are taking like a uranium 90-235. When it is participate alpha decay, what we are getting? Thorium 90-231. So if you are having any confusion, sometimes especially in physics problems, you should remember uranium and all this. Suppose X you can take it, atomic number is the Z and A is the mass number. When it is participating into the alpha decay, here what happens? We are getting the Y element. atomic number is reduced to 2 units and mass number is reduced to 4 units, and this is the alpha. This is the alpha plus some energy you are getting. This is called the alpha decay. And you remember that alpha particles are the positively charged particles. These are having the more ionization, less penetration power. These are affecting both electric and magnetic fields, deflecting in both electric and magnetic fields. These are affecting the photographic plate. Then we are going through the beta decay. Beta decay. When it is participating into the beta decay, no change in the mass number, but atomic number is increased to 1 unit. Beta is nothing but electrons. We can show like this some energy. So these are negatively charged particles. These are also deflecting in both electric and magnetic fields, and these are affecting the photographic plate. But this ionization is less than alpha particle and more penetration comparing with the alpha, not gamma. Suppose they are asking the question like this: X, this is atomic number we are taking like 20, and this is the 48 like that. After that, it is giving that this is the 16 and this is the 40 plus some energy like that. How many number of alpha decays and beta decays are there? Find alpha and beta decay. How many number of alpha particles and beta particles are released? Means look here, 20 minus 16, how much? 4. You know that each alpha particle atomic number is how much? 2. But here 4 means 2 alpha particles it is released. That to mass number also matched. Look here. Here 48 and here 8 difference is coming. So 2 alpha particles. There is no beta particles in this case. Then like that one more problem, like this is the 25 and this is the 42. When it is coming by, this is the 42, this is the 26. So what we are saying, 1 beta particle it is released. Why? Atomic number is increased to 1. So like that depends on the reaction. You should say that how many beta decay and how many beta particles and alpha particles are releasing. Then last one is the gamma decay. What is the gamma decay? Whenever it is participating into the disintegration process, that 2 gamma particles these are releasing, no change in mass number and no change in atomic number. You remember that these are having the velocity is equals to light 3 into 10 to the power of 8 meters per second square. These are not deflected in electric and magnetic fields. So this is about the gamma rays, beta rays and gamma and alpha rays. Then which particles are having the more penetration means you can say that gamma rays, and less ionization also you can say that. Now we are going to discuss about radioactive disintegration or radioactive decay law also we are saying. Radioactive decay law. What is the radioactive decay law? See, radioactive decay law. You know that heavier atoms are participating into the disintegration process. Then these are becomes too stable. But how can we calculate after 1 hour, after 2 hours, after 1 year, after 100 years, after 1000 years, how it is participating into the disintegration process means, just you remember this formula, dN by dt, rate of disintegration is directly proportional to original number of nuclei. If 100 nuclei are there, only 10 nuclei is there. So which one is participating more disintegration? Heavier one. That's why this is directly proportional to this one. Then dN by dt equals to, we are getting minus lambda into n naught. Here lambda is called the disintegration constant. After integration and all this you are getting n equals to n naught into e to the power of minus lambda t. Here n is the present number of nuclei. Then n naught is the original number of nuclei. These are the original number of nuclei. Suppose like that half-life. We are going to discuss about the half-life. So what happens? Original nuclei becomes to half of the nuclei. How much time it will take? That is called the half-life. Simply you can take it, instead of n naught by 2 equals to n naught into e to the power of minus lambda t. Instead of this one you can take it. This one cancel. After integration and all this you are getting t half equals to 0.693 by lambda. Suppose lambda equals to 0.693, example I am giving. So T half equals to how much? T half equals to 1. So if it is 1 year or 1 day, depends on the question, you can get it. So now this is very important formula. And average life. What is the average life? Reciprocal of disintegration constant is called the average life, or the total time taken by that nuclei to participate into the completely into disintegration process, that is called what? Average life. So reciprocal of disintegration constant is called the average life. And you remember that average life and half-life, the relation is T equals to n times of the T half. And here n is the number of half-lives. Number of half-lives, and this is, suppose n equals to 4 and this T half equals to 1600 years. Then what is the average life? So 6400 years. Like that you can calculate. Not only this one, you can remember n by n naught equals to 1 by 2 to the power of n also. Here n is the number of half-lives. Number of half-lives. Suppose original number of nuclei, they are giving some mass like that, and n is the 4. When you are substituting, you can find out the present number of nuclei also with the help of that. Then our next question is the next concept is the what is the nuclear fission? Already I said it is split into two stable nuclei. Then it is giving 200 million electron volts energy, that is called the nuclear fission. But here chain reaction. What is a chain reaction? It is a natural reaction. So here when slowly moving neutron is bombarding with the uranium like that, then it is giving the two stable nuclei along with 3 neutrons, 200 million electron volts energy. So here these 3 neutrons are participating into 3 nuclei, then it is giving the 9 neutrons. Then 9 becomes to 27, 27 becomes to 81. So like the geometrical progression of that releasing of the neutrons is called the chain reaction. So based on that only they have introduced a neutron multiplication factor, number of neutrons in the present situation by number of neutrons in the previous reaction. So if K equals to 1, that is called the controlled chain reaction. We have used, that is the principle of that nuclear reactor. I think you are perfect in that what is a nuclear reactor and what are the parts of that: fuel, control rods, moderators, then the shielding, coolant, all are the parts of the nuclear reactor. If K is greater than 1 means uncontrolled. Here only 1 neutron is participating. Here more than 1 neutron is participating means uncontrolled chain reaction, we can say that. The next one is if K is less than 1 means even single neutron also not participating in the chain reaction. Here we won't observe the chain reaction. So this is about the nuclear reactor. Then already you know that what is the fusion. You can say that lighter new atoms are combined together and it gives the energy, but we can't conduct this one is on Earth. We should provide the 10 to the power of 7 degree Kelvin nearer to the stars and sun only we should observe. And you know that stars are having the self-illuminating power because of the carbon-nitrogen cycle and proton-proton cycle. Okay, thank you everyone. Please subscribe my channel.